Hi everyone, my name is Sorachai Yinjaran from Aalto University. Today I'm going to present Vertex connectivity in poly-logarithmic math flows. This is joint work with Jason Lee, Danupon Nongkai, Devmaya Panikarhi, and Tachapon Salanurak. So first of all, I would like to define vertex connectivity. Given an undirected graph G with n vertices and m edges, we would like to compute the minimum number of vertices to be removed to disconnect the graph. We consider this as kappa G. For example, in this particular graph, the vertex min cut size is 2 because we can remove this 2 node to disconnect the graph, and we cannot remove any other node to just one node to disconnect the graph. Another related notion is that ST connect vertex min cut, which is almost the same, except that we are given S and T as an input. And then we want to compute kappa sub G ST, the minimum number of vertices to be removed to disconnect S and T. So basically to separate S and T in such a way that there is no path from S to T after remove this node. So it is known that computing kappa S and T can be done in time max flow time, in time T flow Mn here. And it is also clear that in order to compute the global minimum vertex cut, is also sufficient to compute ST vertex min cut for all pair ST in all pair of nodes in the graph. So let me tell you more about the current literature of vertex connectivity. So clearly, the trivial algorithm can be done by just calling n square max flow. In the 70s and 80s, there are some improvement by trying to reduce the number of calls of max flow. So this is done by since Kidman 1969, and then in 82, Baker et al. Can reduce the number of calls of max flow to be just order of linear. And then another round of improvement is from algebraic technique by linear Lovatt Richardson in 88, which computes vertex connectivity in time n to the omega plus n times k to the omega, where omega is a matrix multiplication exponent. And then the next improvement is done by Heisinger, Rao, and Gabel in 96, which gives mn times algorithm for computing vertex connectivity. One remark here is that this is also another max flow based algorithm. The main difference from previous is that previous max flow based algorithm is that this is a white box, in a sense that they modify the pre-flow algorithm in such a way that it works for vertex connectivity. And then this is it for the, meaning that the running time Mn is the best known bound so far. And then there's no much progress here since 96. But if you compare to the sibling problem like ST vertex max flow, ST vertex connectivity, or like max flow, there are some exciting progress in the field. For example, in unit capacity max flow algorithm based on interior point method and more sophisticated technique. The most recent work now, they can solve max flow in m plus to the n to the 1.5. This is near linear for dense graph. And then there's another algorithm that it fast for the sparse graph with the running time m to the 4/3, roughly. The interesting point here is that even though there are some progress in max flow algorithm, this progress generally do not transfer to vertex connectivity algorithm. So basically the new result do not transfer. And then in particular, the bound Mn stands, even though we, let's say we assume very strong assumption that we can have linear time max flow and even omega equal to 2. Then we don't know how to break this bound. However, there are some good progress in recent years. Some recent progress happened when you consider small connectivity. If the input graph has some connectivity small, then yeah, we can break. So in the based on the local flow, local algorithm, the first work is done by NSY in 2019, and then in 2020, there's another algorithm that is like near linear time when k is like constant, for example. However, with this recent progress, the MN barrier still stands when connectivity is large. It's larger than a square root n in particular, and then what we have in this paper is the following: is that the main result is that if max flow can be solved in m to the x time, then there is a m to the x time randomized vertex connectivity algorithm, meaning that we have only poly-logarithmic overhead in the running time here. So here's an interesting implication. First, currently x is equal to 4/3, meaning that we can break mn unconditionally at this point. And then faster max flow algorithm will imply automatically a faster vertex connectivity algorithm because we have a full reduction here. And in particular, if the max flow is linear, then it would resolve a long-standing conjecture given by Aho, Hofgrove, and Ullman since 1974 about the existence of linear time algorithm for vertex connectivity. So if you look at the picture in the how does it fit into the picture, here is that this paper will give full reduction to max flow. So the only one caveat here is that the running time here is going to be flow of m sub m, and then currently, which means that we could not apply the algorithm for the dense graph because the running time would be run of the form m to the 1.5. But when we apply the formula for the running time for the sparse algorithm for the sparse graph, then the running time we get is going to be m to the 4/3, which is sub mn, and this means that we break mn running time. So what is the key technique? So one way to build this new idea is that in the previous approach, they try to generate many instances of max flow, and then each instance has size linear. And then the goal is to minimize number of calls to max flow, right? And then the best known number of calls is linear, and this is the best known number of calls that we can do. What we do differently in this work is that instead of generating instance of size m, we just allow the size to be any size. As it can be very small, but as long as the total size is near linear, then we are good. So here is what we do. So we just focus on generating many instances of max flow. So that's in such a way that total instances is near linear. Okay. So in particular, some instance can be very small, and so that will conclude. Then let me say the main result more precisely. So basically, we have a randomized vertex connectivity algorithm that makes max flow call of total number of vertices to be m, total number of edges to be m as well, and then the algorithm would take only near linear time outside max flow call for this full reduction. And one more remark is that all techniques can be extended partially to get a directed version as well, which run faster in this run sub mn time. Okay. So they concluded the introduction. Now I want to tell you more about the techniques that we have. So for simplicity, let's assume that the input graph G has connectivity very high. Okay, this is because the small connectivity we know how to do in sub mn. So let's focus on the very high connectivity, and also assume for illustration here that we know the linear time max flow. There's a linear time max flow algorithm, and I'm going to show you how to compute vertex connectivity in near linear time. Okay, so So now let's assume that we fix some optimal separator of size n, and then this sub separator we consider like the left side, the middle side, and the right side. What we do here, the technique is called kernelization. So basically, it's a pre-processing by doing some contracting and then removing edges, removing nodes, and then so that the resulting graph has some very small, so very small, and still preserves the connectivity somehow. But we want to make sure that the total size is also near linear. Next, I'm going to tell you about the kernelization. So I will show you by example. So let's say that this particular graph, I want to compute max flow from S to T. Okay. So what would be the min cut from this graph? So for example, the min cut would look like this, that has this L, S, and R that separate in this way. So S is the minimum separator that separate S and T. Okay. So here is the execution of the kernelization. So what happened is that first we contract some subset of R. In this case, one subset would be something like this node T and this node bottom here in R. So we contract this node inside of R, and then what happened here is that the optimal separator still remains in this resulting graph. In the next step, we're gonna remove the neighbors, the edges between the neighbor of this T and the edges between the neighbor of S from the sink, the edges inside the neighbor of sink, and then the edges inside the neighbor of source. For in this particular graph, I will remove this triangle here, these three edges, and then the resulting graph would look like this. And furthermore, we can also remove this dangling node as well. The reason that we can remove these edges inside is because that the maximum flow would not use any edges that consider inside between neighbor of T and neighbor of S. And the same reason here, the max flow will not use this node at all, because once you reach to the sink, then there's no reason to go back to this node. So that's the high level idea. And then this is the resulting graph, and you can see that ST min cut is preserved in this graph, and then we can run max flow on this smaller graph, and then we can obtain the corresponding separator to the original graph. So there are two things remain unclear. First, how large do we need to reduce, how to get rid of the unused edges? What would be the appropriate size of the kernel? And also another challenge is that we don't know the set R to begin with. How do we handle this? Then there are two things in mind. Okay, before that, I would like to give a preliminary to state a little bit more precisely. So I want to tell you the notation about this. So first, I consider vertex cut L, S, and R. And we call S to be XY separator if when I remove S from the graph, it separates X and Y. And then this separator vertex cut X, and we assume without lot of generality that L is smaller than R, because otherwise I can just switch L and R. And I also define X sub capital T separator, where the capital T is basically a subset. So basically, S is a X sub capital T separator if when I remove S, then there is no path from X to any node in T. So that's what I mean by X sub T separator. One important observation from the highly connected graph is that it's dense, because we can observe that the minimum degree is at least K, where K is the connectivity. And this is because if the minimum degree is smaller than K, then I can just output that vertex, minimum vertex, the min degree node, and then at the neighbor of min degree node, then I would get the smaller cut. So now, because we assume that the connectivity is very high to be linear, then we have the total size to be n squared. Next, I'm going to tell you the idea how to compute vertex connectivity. So consider fixed and optimal separator L, S, and R, where X is in L. So let's assume somehow we know X is in L, okay? And then here's a step of the kernelization. We want to transform graph G. This is the original input graph into some graph H, where such that, so that it's preserved xt minimum separator in H. Xt minimum separator in H is an xt capital T minimum separator in G. And I want this graph to be of size ML. And from here, small t is a sink in H, and capital T is the given vertex set in G. We want this kernelization to be done in NL time. Okay. So to give an idea how this kernelization can even exist, so consider the following example. So we first contract capital the node R into some node, a small node R right here, and then we remove edges inside S. And then the claim is that the minimum separator that separates X and R in this graph is the minimum X separator in the original graph. This is easy to see because MacFlow doesn't use edges inside the neighbor of the sink, so we can remove edges inside here. And so H is the kernel of this graph. If you look at this formula, we consider T to be R, and then capital T will be capital R in this set. In this case, what will be the size of this kernel? So the size of this graph is the number of edges of this graph is gonna be L squared plus L times S. And then there's no edge inside S because we remove it all, right? And then the edge from S to R to B. Then the total number of edges is just NL. So let's see how would this be useful. Suppose somehow we obtain this kind of kernel in NL time somehow. And then here's a full algorithm to compute vertex connectivity. First, compute X in L. How to compute X in L? We just sample a vertex randomly. So if I sample a random vertex, then the probability that that vertex belongs to L is going to be L over N. Okay, so I need to sample that N over L times in order to get an event where X is in L. And then when X is in L, then I can compute the kernel using the above property, and then just call MacFlow on this kernel. And then I can obtain the minimum cut. How long does it take? It's gonna take N over L time, because I need to sample N over L time to get the event X in L in with high probability. And then for each time I compute kernel and run MacFlow, right? So the total running time will be N squared. And this is near linear. So what if this is possible that there's some event that X is not in L. In that case, the kernel will be the kernel of different separator, but it's okay because we want to compute the minimum cut. So it's just we take minimum of the cut that we obtain from this kernel. Okay, and finally, I want to mention that last issue is that we don't know capital R, right? So for this one, we kind of contract R into the small r. How do we handle this case? So in our paper, what we do is the following. We do the following. We do the following. We remove, we replace with this. So what we do is that instead of contracting R, which we don't know, we just sample a random subset of Tx such that Tx is in R. So in this case, we want T sub x to be in R with constant probability. And then we contract TS into a single vertex T. And then we remove some edges, some vertices in a similar manner in the example. And then let H prime to be remaining graph. The claim is that with high probability, we will get this kernel, and then the kernel size will be NL. And we can construct this in NL time. So this concludes the high-level idea of how to obtain LT call to compute vertex connectivity in near linear time. So one remark is that it's not. So we need to also efficiently construct the kernel, which is because we cannot afford to touch all edges. And for example, even for this two neighbor away from the source node, can already have like a lot of edges at order of n square. We cannot afford to touch edge inside the neighbor of x because we plan to remove this guy, this red edge inside. The solution that we do in the paper is that we use linear sketching and sparse recovery techniques from streaming and signal processing community to list element outside of the neighbor of x in log time, in log n time, and then to also estimate the size of the neighbor that go outside of v in log n time. Okay, so let me briefly mention how to handle general case for vertex connectivity. In general, we have a parameter k, which is the target vertex cut size. We consider two cases, one unbalanced and balanced. For the balance, we define to be like the size L is smaller than k. In this case, we use the same kernelization technique, but we require more we want to improve the kernel of size KL plus some technical condition, and then instead of NL. And then we handle the technical condition in the balance case. For the balance cut, we define L to be greater than K. We use isolating vertex cut lemma, which we adjust from isolating edge cut lemma from previous work. And it's basically say that if you can sample a success of vertices in such a way that one node in the sample is in L, nothing in S, something in R, then in poly-logarithmic max flow time, you can get the minimum cut. So this concludes the idea, this concludes the high-level approach. And the key message here is that if you want to do the full reduction to max flow, it's also enough to just produce many instances of the smaller size or big size of total size to be near linear. And I would be very happy to take your question in the session.